Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight. Before we begin our journey through one of the strangest questions in modern astronomy, I'd love to know, where in the world are you watching from? A quiet bedroom as the stars come out? A cosy corner where the day is finally winding down? Wherever you are, I hope you're comfortable, safe, and ready to drift gently into contemplation. And here's a question worth pondering as you settle in. Do you ever wonder if something out there is watching back? If our presence on this small blue planet has been noticed by the vast dark universe surrounding us? If you enjoy these calm explorations of cosmic mysteries and would like to hear more, a like and subscribe really helps this channel reach others who are seeking the same peaceful way to end their day. And to those of you already subscribed, thank you. Truly, your support means more than you know. Now, tonight's topic might sound dramatic at first. We're going to talk about a comet, an interstellar visitor called 3I/ATLAS, and we're going to explore a question that sounds like it belongs in science fiction. Could we have accidentally triggered its arrival? Could humanity's electromagnetic noise, our radio broadcasts, our nuclear tests, our deliberate messages to the stars, could any of this have attracted an object from another star system? But don't worry, this isn't going to be a countdown to catastrophe or a breathless scramble through conspiracy theories. Instead, we'll move slowly and carefully through what we know, what we think we know, and what remains beautifully uncertain. We'll explore the science of how signals travel through space, the timeline of humanity's cosmic footprint, and the mathematics of coincidence versus causation. And by the end, I think you'll find that whether we triggered anything or not, the story of our growing cosmic presence is profound, peaceful, and worth contemplating. So settle in, let your shoulders drop, take a slow breath. And let's begin our slow drift through the story of what happens when a civilization starts making noise in the cosmic dark. To understand whether we could have triggered anything, we first need to understand what arrived. On April 5th, 2024, astronomers working with the Atlas Survey in Hawaii noticed something unusual in their images of the night sky. It appeared as a faint, fuzzy smudge moving against the background of stars. Not a star itself, which would remain fixed. Not an asteroid, which would be too sharp-edged and bright. This was something else, something with the characteristic glow of a comet surrounded by a halo of gas and dust. They designated it C/2024 G3, Atlas, following the standard naming convention for comets. The quote 0 meant it was a comet. The quote 1 told you when it was discovered and that it was the third comet found in that particular period. And quote 2 identified the survey that spotted it. But as more observations came in, as telescopes around the world turned their attention to this new visitor, something remarkable became clear. This wasn't just another comet from our solar system's distant reservoirs. The trajectory calculations showed something unusual. The orbit wasn't elliptical, bound to our sun in an endless loop. It was hyperbolic, open-ended, which meant this object had come from somewhere else entirely. It was an interstellar visitor, only the third one ever confirmed. The first interstellar object we detected was Oumuamua, that strange elongated visitor that passed through our solar system in 2017, tumbling end over end, accelerating slightly as it left in ways that sparked endless speculation about its nature. The second was 2I/Borisov, a more conventional-looking comet that arrived in 2019, complete with a visible tail and behaviour that matched our understanding of how comets should act. And now, 3I/ATLAS, the third messenger from the space between stars. The calculations showed it had entered our solar system from the direction of the thick disk region of our galaxy, that band of older stars that forms a flattened sphere around the Milky Way centre. It was moving at roughly 30 to 50 kilometres per second, a speed consistent with objects drifting through interstellar space, their velocity shaped by gravitational encounters with stars and clouds of gas over millions of years. Its trajectory would bring it to perihelion, its closest approach to the Sun, on January 13th, 2025. At that point, it would be approximately 0.13 astronomical units from our star. 1 astronomical unit is the distance from Earth to the Sun, about 150 million kilometres. So 0.13 AU places the comet roughly 19.5 million kilometres from the Sun, well inside the orbit of Mercury. At its closest approach to Earth, 3I/ATLAS would be approximately 1.5 astronomical units away. That's 225 million kilometres, or about 140 million miles, farther than the Sun is from us, far enough that it poses absolutely no threat, but close enough that we can study it in detail, gathering data that might tell us about the chemistry and conditions around other stars. Spectroscopic analysis, the process of splitting the light from the comet into its component wavelengths to identify what molecules are present, revealed something intriguing. The comet's coma, the glowing cloud of gas surrounding its nucleus, showed an unusually high ratio of carbon dioxide to water. Most comets in our solar system are dominated by water ice, with carbon dioxide present but secondary. 3I/ATLAS seem to have about 8 times as much carbon dioxide as water. That unusual composition sparked questions. Did it form in a colder region of its home star system, where carbon dioxide could freeze more readily than in the regions where our solar system's comets formed? Was it older, perhaps, having already lost much of its more volatile water ice during previous passes near other stars? Or did it simply come from a system with different chemical abundances, a star with less oxygen or more carbon in its protoplanetary disk? There was another curiosity. The comet began outgassing, releasing gas and dust at approximately 4.4 astronomical units from our Sun. That's farther out than most comets typically become active. Usually comets don't start showing significant activity until they get within about 3 astronomical units, roughly the orbit of the asteroid belt. The early activity suggested that 3I/ATLAS contained particularly volatile ices, compounds that could sublimate, turn directly from solid to gas, at lower temperatures than water ice. All of this data, all of these observations, painted a picture of an object that was genuinely from elsewhere, a wanderer that had been drifting through the galaxy, perhaps for millions of years until gravity gently guided it toward our Sun, a visitor that would pass through our solar system once, briefly warming in our star's light and then head back out into the cold and dark, never to return. That, at least, is the straightforward interpretation. An interstellar comet, ejected from its home system by gravitational interactions with planets or stars, now making a one-time passage through our neighbourhood. Natural, explicable. Requiring no special circumstances beyond the ordinary dynamics of a galaxy filled with stars and planets and the debris of their formation. But there's something about the timing that gives some astronomers pause. Not alarm, just a quiet curiosity, a wondering. 3I/ATLAS arrives during a very specific window in human history, a window that began roughly a century ago when we started making a particular kind of noise, the kind that travels through space at the speed of light, the kind that announces to anyone with the right technology to detect it that something intelligent exists on a small planet orbiting an unremarkable yellow star. Could that be coincidence? Almost certainly yes. The galaxy is vast. Interstellar objects are probably far more common than we realise. We're only now developing the telescopes sensitive enough to spot them. The timing could simply be random chance, an interesting overlap with no deeper meaning. But it's worth asking the question, worth exploring calmly and carefully what it would mean if the timing weren't random. Worth understanding what we've been broadcasting into the cosmos for the past 100 years and whether any of it could have been noticed. Because whether it attracted 3I/ATLAS or not, one thing is certain. We are no longer cosmically invisible. We have made ourselves known, and that fact alone, regardless of who might or might not be listening, changes our relationship with the universe in ways both subtle and profound. For billions of years, Earth was electromagnetically silent. The planet existed, of course. It rotated, it orbited, it generated a magnetic field from the churning of its molten core. Lightning crackled through its atmosphere, creating brief radio bursts. The aurora danced at the poles. Charged particles from the sun interacting with the magnetosphere. But all of this was natural, background noise, the kind of electromagnetic activity that any rocky planet with an atmosphere and magnetic field might produce. There was nothing in Earth's electromagnetic signature that would indicate intelligence, nothing that would stand out from the general hum of natural processes occurring on millions of worlds throughout the galaxy. And then, in the late 1800s, something changed. Guglielmo Marconi, working in Italy and England, developed a practical system for wireless telegraphy. Nikola Tesla, in his laboratory in Colorado Springs, conducted experiments with high-frequency alternating currents and electromagnetic waves. Heinrich Hertz had already demonstrated that electromagnetic waves could be generated and detected, proving the theoretical work of James Clerk Maxwell. But it was the inventors and engineers of the 1890s and early 1900s who turned those discoveries into technology. Radio was born. The first transmissions were weak. Morse code signals sent across short distances, measured in miles rather than hundreds of miles. The electromagnetic waves they produced leaked into space, certainly, but at intensities so low that they would be indistinguishable from background noise within a few light years. But the technology improved rapidly. By the 1920s, commercial radio broadcasting had begun. On November 2nd, 1920, KDKA in Pittsburgh, Pennsylvania, broadcast the results of the presidential election. It's often cited as the first commercial radio broadcast in the United States, though other stations and countries have their own claims to priority. Regardless of who was truly first, the 1920s marked the beginning of continuous powerful radio transmissions from Earth. AM radio stations proliferated. By 1925, there were hundreds of stations across North America and Europe, each one broadcasting music, news, entertainment, advertisements, each one sending electromagnetic waves in all directions, including up, into space, where they continued travelling, unimpeded, at the speed of light. The 1930s brought television. The BBC began regular TV broadcasts in 1936. NBC and CBS followed in the United States. Television signals, being higher frequency than AM radio, required more power and were even less efficiently contained by Earth's atmosphere and ionosphere. They leaked into space more readily. Then came World War II, and with it, radar. Military radar systems designed to detect aircraft and ships operated at even higher frequencies and powers. These were some of the strongest electromagnetic signals Earth had ever produced. Pulses of radio waves bouncing off objects and returning to receivers, allowing operators to see what the eye could not. But those pulses didn't stop when they missed their targets. They kept going, out into space, travelling forever, or until they encountered something that absorbed or scattered them. By the end of the 1940s, Earth was no longer electromagnetically silent. We had become loud. Unintentionally, without thinking about the cosmic implications, we had started advertising our presence to the universe. It wasn't like turning on a single light in a dark room. It was more like slowly increasing the brightness over decades. In 1920, we were a dim bulb. By 1930, we were brighter. By 1940, brighter still. And the intensity kept increasing as more radio stations came online, as television spread across continents, as radar installations multiplied for military and civilian use. Imagine Earth from space during this period. For billions of years, it would have looked like any other planet, reflecting sunlight, emitting infrared radiation from its warmth, its magnetic field deflecting the solar wind. Then, beginning around 1920, it started to glow faintly in radio wavelengths. A new kind of light, not natural, not from any known physical process except the deliberate manipulation of electromagnetic fields by technology. By 1950, anyone with a sufficiently sensitive radio telescope pointed at Earth from a nearby star would have known something unusual was happening on that planet. The signals would be weak after travelling light years, certainly, but they would be there, and they would be distinctly artificial. Random noise has a characteristic signature, its broad spectrum, evenly distributed across frequencies, following predictable patterns dictated by physics, but our broadcasts weren't random. They were structured, amplitude modulation and frequency modulation creating patterns in the radio waves, television signals encoding images through careful manipulation of signal strength and timing, radar pulses sharp and regular, unmistakable in their artificial precision. These weren't the electromagnetic whispers of lightning or aurora. These were organised, intentional, technological. We didn't mean to send them into space. We were just communicating with each other. Broadcasting entertainment, coordinating air traffic, tracking weather systems. But the laws of physics don't care about intent. Electromagnetic waves travel in all directions from their source, unless specifically directed. And even directed signals have side lobes and scatter. Some energy always escapes, so for a century now, give or take a few years depending on where you mark the beginning, we've been creating an expanding bubble of electromagnetic noise. A sphere, centred on Earth, growing outward at the speed of light, every broadcast, every transmission, every radar ping adding to the signal. That bubble has consequences, not dangerous ones, not harmful, but consequences nonetheless. Because once you send a signal into space, you can't take it back. It's out there, travelling, carrying information about its source, about us, and the bubble keeps expanding. Every year it grows by 1 light year in radius, every decade by 10 light years. The signals from the 1920s are now over 100 light years away, having passed thousands of stars. The signals from the 1950s are 75 light years out. The signals from the 1980s, when personal computers and cell phones started to proliferate, are 40-some light years distant. We didn't plan this. We didn't sit down as a species and decide to announce ourselves to the cosmos. It happened because we wanted to listen to baseball games and watch television shows and coordinate airline flights. But the effect is the same. We became visible. We became loud. We created a signature that any sufficiently advanced technology could detect and recognise as artificial. And that bubble, that expanding sphere of electromagnetic noise, is still growing, still carrying the sound of our existence deeper into the galaxy. Still announcing to anyone who might be listening that something on Earth has learned to manipulate electromagnetic fields with purpose and structure. Whether anyone heard is another question, but the signals are there, travelling through the dark, carrying pieces of us, our music, our voices, our attempts to communicate and understand, farther from home than any human will ever travel in person. When a radio wave leaves Earth, it doesn't stop. It doesn't slow down or decay, at least not in the way that sound waves do in air, weakening and dispersing as the molecules of the medium absorb their energy. In the vacuum of space, electromagnetic waves travel essentially forever. They spread out, yes. They weaken with distance, certainly. But they continue at the speed of light until something stops them. This creates what astronomers sometimes call Earth's electromagnetic bubble. A sphere of radio and television signals, radar pulses and microwave transmissions, expanding outward from our planet at 299,792 kilometers per second. That's the speed of light. Roughly 300,000 kilometers every second. About 9.5 trillion kilometers per year. 1 light year. So the signals we broadcast in 1920 have travelled approximately 104 light years by now. They've passed through the space occupied by an estimated 15,000 stars. Some of those stars have planets. We know that now from decades of exoplanet discoveries. Statistically, some of those planets are likely rocky, Earth-sized, in the habitable zones of their stars where liquid water could exist. Some might even have atmospheres, oceans, life. The signals from 1945, when World War II ended and radar was at its most powerful, have travelled 79 light-years. The signals from 1975, the height of the Cold War, when global telecommunications were expanding rapidly, have travelled 49 light-years, and the signals from 2024 are just leaving the immediate neighbourhood of our solar system, a few light-hours out, passing the orbit of Neptune. But here's where the physics gets important. Those signals aren't staying strong. As they travel, they spread out, and this spreading weakens them according to a principle called the inverse square law. Imagine a light bulb shining in a dark room. Right next to the bulb, the light is intense. Move 1 meter away, and the same amount of light is now spread over a sphere with a radius of 1 meter, a surface area of about 12.5 square meters. Move 2 meters away, and the light is spread over a sphere with a radius of 2 meters, a surface area of about 50 square meters. 4 times the area, 1/4 the intensity. That's the inverse square law. Intensity decreases with the square of the distance. Double the distance, 1/4 the intensity. Triple the distance, 1/9 the intensity. 10 times the distance, 1/100th the intensity. For radio signals, this means that while they continue travelling forever, they become extraordinarily faint extraordinarily quickly. A television broadcast from the 1960s, which seems so bright and powerful here on Earth, powerful enough to reach millions of homes, is incredibly weak by the time it's travelled even a few light-years. By the time that signal reaches Alpha Centauri, our nearest stellar neighbour at 4.3 light-years, it's been diluted over a sphere with a radius of 4.3 light-years. The intensity is roughly 1/18th as strong as it was at 1 light-year. By the time it reaches a star 50 light-years away, it's been diluted by a factor of 2,500. At 100 light-years, by a factor of 10,000. This doesn't mean the signal disappears, it just means it becomes harder and harder to distinguish from background noise. The cosmic microwave background, the faint remnant glow of the Big Bang itself, fills all of space with a low level of electromagnetic radiation. Other stars emit radio waves. Pulsars send out regular pulses. Supernova remnants create radio noise. Our Milky Way galaxy as a whole produces a background hum of electromagnetic energy. Against all that noise, a television broadcast from Earth, weakened by distance, starts to blur into invisibility. But, and this is crucial, it doesn't become impossible to detect, just difficult. Very difficult, certainly, without extraordinary technology, but not impossible. Consider what we can already do with our current technology. The Arecibo radio telescope, before its collapse in 2020, was sensitive enough to detect incredibly faint signals. If there were another Arecibo-class telescope orbiting a star 50 light-years away, and if it were pointed directly at us, and if it were listening at the right frequencies, it could theoretically detect our strongest radar transmissions, not our normal radio broadcasts. Those would be too weak. But military radar, air traffic control radar, the big phased array systems designed to track satellites and missiles, those are powerful enough to be detectable across interstellar distances if someone is actively looking for them. Now imagine a civilization with technology not just equal to ours, but centuries or millennia ahead. Imagine radio telescope arrays not just comparable to Arecibo, but orders of magnitude larger and more sensitive. Networks of receivers spread across star systems, working together to amplify faint signals. Signal processing algorithms that can pull coherent patterns out of noise we couldn't even detect. Artificial intelligence that can recognize the structure of an artificial transmission even when it's buried deep below the threshold of random fluctuation. With that kind of technology, Earth's electromagnetic bubble would be quite visible indeed. Out to perhaps 100 light-years, maybe more, our presence would be detectable to anyone specifically searching for it. Not easy to find, necessarily. Space is vast. There are many directions to search, many frequencies to monitor, but findable. noticeable, recognizable as artificial once you spotted it, and the bubble keeps expanding. Every second it grows by 300,000 kilometers in all directions, every year by nearly 10 trillion kilometers, in a century by about 100 light years. The signals from the 1920s are now reaching stars we've barely catalogued, systems we know almost nothing about, worlds we've never imagined. Some of those signals are carrying music, jazz from the 1920s and 1930s, big band swing from the 1940s, rock and roll from the 1950s and 1960s, the Beatles eventually, Mozart and Bach and Beethoven broadcast on classical stations, the human voice reading news, telling stories, performing plays, making jokes, advertising products we no longer remember. Some are carrying images, the first fuzzy black and white television pictures, Milton Berle and Lucille Ball, the moon landing broadcast in 1969, seen by hundreds of millions and simultaneously transmitted into space. Images of Earth, of humans, of our cities and technologies and faces. Some are carrying pure information, binary data from early computer networks, evolving into the complex protocols of the internet, scientific data transmitted between observatories, military communications encrypted but still artificial in structure, all of it travelling outward, all of it creating a historical record of human technological development, preserved in electromagnetic form, moving through the galaxy. A time capsule that we never intended to create, but created nonetheless, just by being who we are and doing what we do. And at the centre of this bubble sits Earth, still broadcasting, still adding to the signal, still making noise in the cosmic dark. Not because we're trying to be found, necessarily. Not because we've made some conscious decision to advertise our presence. But because that's what technological civilizations do. They produce electromagnetic radiation as a side effect of their technology. And once you start, you can't really stop. Not without abandoning the very technologies that make modern life possible. So the bubble continues to expand, a sphere of noise growing at the speed of light, carrying the sound of humanity deeper into the galaxy with every passing second. Carrying our music and our voices and our attempts to communicate, preserved in waves of electromagnetic energy, travelling forever or until they meet something that can receive them. Whether anyone's listening remains unknown, but the signals are there, real, travelling, waiting. On July 16th, 1945, at 5:29 in the morning, in the desert of New Mexico, humans did something they had never done before. They split the atom, deliberately, violently, in a carefully engineered explosion that released energy on a scale previously reserved for the cores of stars. The test was called Trinity. The device was a plutonium implosion bomb. The culmination of years of secret work by the brightest physicists of the era, racing against the possibility that Nazi Germany might develop the same technology first. It was detonated atop a steel tower in a remote section of the Alamogordo bombing range, miles from the nearest town, in terrain so empty that it seemed appropriate for testing something so powerful and new. The explosion released energy equivalent to about 22,000 tons of TNT. A fireball brighter than the sun rose into the pre-dawn darkness. A mushroom cloud climbed to nearly 40,000 feet. The flash was visible from nearly 200 miles away. Windows broke in buildings 100 miles distant, and the desert sand beneath Ground Zero melted into a pale green radioactive glass that scientists later named Trinitite. But there was another effect. Less visible, but perhaps more significant for our purposes. The explosion created an electromagnetic pulse, a burst of gamma rays and X-rays that interacted with the atmosphere to generate powerful electromagnetic fields. Radio waves across a broad spectrum, a flash of energy that, like all electromagnetic radiation, didn't stop at the edge of the atmosphere. It continued outward, into space. This was different from our radio broadcasts and radar signals. Very different. A nuclear explosion has a distinctive electromagnetic signature unlike anything natural. Supernovae create gamma-ray bursts, certainly. Pulsars and black holes and other exotic objects produce high-energy radiation. But the specific pattern of a nuclear fission explosion, the rapid assembly and disassembly, the particular isotopes involved, the characteristic timing and spectrum, this is unique to artificial devices. Anyone with sensitive enough instruments watching from space would know immediately that what they were seeing wasn't natural. The signature would be clear, unmistakable. This was technology. This was a civilization that had learned to manipulate the binding energy of atomic nuclei. This was dangerous, sophisticated, deliberate. Trinity wasn't alone. 3 weeks later, on August 6th, an atomic bomb destroyed Hiroshima. On August 9th, another destroyed Nagasaki. World War II ended. The nuclear age began, and humanity entered a period where the testing of these weapons became almost routine. The United States conducted over 1,000 nuclear tests between 1945 and 1992. The Soviet Union conducted more than 700. The United Kingdom, France and China added hundreds more. Some were underground, contained within chambers carved into rock, their effects mostly trapped below the surface. But many, especially in the early decades, were atmospheric tests. Detonated in the air or on towers, or dropped from aircraft or launched on missiles to explode at altitude. Each atmospheric test created another flash, another electromagnetic pulse, another signal travelling out into space at the speed of light, carrying with it the unmistakable signature of nuclear technology. The largest test ever conducted was Tsar Bomba, detonated by the Soviet Union on October 30th, 1961. 50 megatons, 50 million tons of TNT equivalent, a fireball 5 miles wide. A mushroom cloud that reached 40 miles into the stratosphere, a flash visible from 600 miles away, and an electromagnetic pulse that almost certainly made Earth briefly visible to any sufficiently advanced observers within hundreds of light years. These tests tapered off after the Partial Test Ban Treaty in 1963, which banned atmospheric, underwater, and space testing. Most nuclear testing after that point went underground, where the electromagnetic effects were largely contained. But the damage, in terms of cosmic invisibility, was already done. Decades of atmospheric tests had sent a clear signal into space. This planet has nuclear weapons. This civilization has harnessed the atom. This is either very impressive or very concerning, depending on your perspective. There's something poetic and terrifying about the idea that our most destructive technology might also be our brightest beacon, that the weapons we built to threaten each other might be what announces us to the cosmos, that the flash of annihilation could be the first thing another civilization notices about us. But it's not just the electromagnetic pulse. Nuclear explosions produce other detectable effects. They emit neutrinos, those ghostly particles that barely interact with matter, streaming out from the reaction at nearly the speed of light. They create specific isotopes that don't occur naturally in significant quantities, radioactive elements that could theoretically be detected in the solar wind or in samples of interstellar dust. They alter the chemical composition of our atmosphere in subtle but measurable ways. All of this combines to create what astrobiologists call a technosignature, a sign of technology, an indicator that a planet hosts not just life, but intelligent. Tool using life capable of complex engineering, and nuclear technology is one of the clearest technosignatures imaginable, because there's simply no natural process that produces quite the same results. It's worth noting that while the electromagnetic pulse from a nuclear explosion is powerful, it's also brief. A flash lasting seconds or fractions of seconds, then gone. This is very different from the continuous broadcast of radio and television, which provides a sustained signal over decades. A civilization would have to be watching at exactly the right moment, or have instruments capable of detecting and storing such brief events to catch the flash from a nuclear test. but the cumulative effect of hundreds of tests spread over decades increases the probability that someone somewhere might have noticed. Each test is another chance, another flash in the dark, another signal saying, "We're here and we've figured out how to split the atom." And of course, we haven't stopped making nuclear technology. It's transitioned from weapons testing to power generation. Nuclear reactors around the world produce energy through controlled fission, releasing neutrinos as a byproduct. These neutrinos stream out continuously, in quantities far exceeding natural background levels. An advanced civilization with neutrino detectors, a technology we're only beginning to develop ourselves, could potentially identify Earth as a source of artificial neutrino production from interstellar distances. So the nuclear age added another layer to our cosmic footprint. Not just electromagnetic noise from communications, but the distinctive signature of nuclear physics. Not just quote 3, but quote 4, a different kind of message, a more complex one. Saying something about our technological development, our scientific understanding, and perhaps our relationship with power and danger. The signals from Trinity in 1945 have now travelled 79 light years. They've passed hundreds of stars. Anyone watching from within that radius would have seen Earth suddenly develop a new kind of light in July 1945. A flash that said something important had changed on that small planet. A flash that announced, whether we intended it or not, that human civilization had reached a new threshold. And those signals, like all electromagnetic signals, keep travelling. The flash from Trinity is still moving outward, still carrying its message, still saying, to anyone with the technology to detect it, something interesting is happening here, something worth paying attention to. For the first 70-some years of the radio age, our electromagnetic signals leaked into space unintentionally. We were communicating with each other, not with the cosmos. Our broadcasts were side effects, not deliberate messages. But on November 16th, 1974, that changed. On that day, astronomers at the Arecibo Observatory in Puerto Rico did something unprecedented. They aimed the telescope, at the time the largest radio dish in the world, 305 metres across, carved into a natural sinkhole in the jungle, at a point in the sky where a globular cluster called M13 hangs in space, and they transmitted. Not a routine signal, not a communication with a satellite or spacecraft, a message, deliberate, structured, designed specifically to be understood by anyone who might receive it. The message was relatively short by broadcasting standards, 1,679 binary digits, ones and zeros, transmitted at a frequency of 2,380 megahertz. The choice of frequency wasn't random. It's close to the emission frequency of hydrogen, the most abundant element in the universe, a wavelength that any civilization interested in radio astronomy would likely monitor. The choice of 1,679 digits was also deliberate. That number is the product of two prime numbers, 23 and 73. Prime numbers are special because they are only divisible by themselves, and any civilization capable of detecting the signal would presumably understand mathematics and would recognize that 1,679 factors into primes in only one way. This gives a hint about how to decode the message. If you arrange 1,679 digits into a rectangle, there are only two ways to do it that result in neat rows and columns, 23 rows of 73 digits, or 73 rows of 23 digits. One of those arrangements makes sense, the other produces gibberish. A civilization receiving the message would presumably try both and recognize which one revealed the pattern. When you arrange the message correctly, 73 rows of 23 digits, and interpret the ones and zeros as black and white pixels, an image appears. A simple pixelated picture conveying several pieces of information about humanity and Earth. At the top are the numbers 1 through 10, represented in binary, a way of establishing our mathematical understanding and showing how we count. Below that, the atomic numbers of 5 key elements: hydrogen, carbon, nitrogen, oxygen, and phosphorus. The building blocks of life as we know it, arranged to show that we understand chemistry and atomic structure. Next comes the structure of DNA, a simple schematic showing the double helix, the sugar phosphate backbone, the base pairs, an indication that we understand the molecule of heredity, the code that carries biological information from one generation to the next. Then, a crude stick figure of a human. Bipedal, 2 arms, a head. Next to it, a number indicating the average height of a human in units based on the wavelength of the transmission. And another number indicating the human population of Earth at the time, about 4 billion. Below the human figure is a simple diagram of the solar system. 9 planets. Pluto was still considered a planet in 1974, with the third one, Earth, offset slightly to indicate that this is where the message originates. Our home, our place in space. And finally, at the bottom, a schematic of the Arecibo telescope itself. The tool we use to send the message, illustrated with simple lines showing its parabolic shape and indicating its size. The entire message, transmitted at high power, took less than 3 minutes to send, and then it was done, launched into space travelling at the speed of light, aimed at M13. M13 is a globular cluster in the constellation Hercules, about 25,000 light-years away. It contains roughly 300,000 stars packed into a region about 150 light-years across. A dense congregation of ancient suns, formed early in the galaxy's history, orbiting together in a spherical swarm held by mutual gravity. The message won't arrive for 25,000 years. By the time it reaches M13, human civilization will likely be unrecognizable, if it still exists at all. And if anyone there receives it and sends a response, that response won't arrive back at Earth for another 25,000 years, 50,000 years round trip, far beyond any practical timescale for conversation. So in one sense, the Arecibo message was symbolic, a gesture, a way of saying, as a species, that we're here and we're trying to communicate. A message in a bottle cast into an ocean so vast that we'll never know if anyone finds it. But in another sense it was significant because it marked a shift in intent. We were no longer just leaking signals into space. We were deliberately reaching out, consciously attempting contact. And while the Arecibo message was a one-time event, it represented a new way of thinking about our relationship with the cosmos. It wasn't the only deliberate message we've sent. In 1999 and 2003, a project called Cosmic Call transmitted messages towards several nearby stars using the Evpatoria RT-70 radio telescope in Ukraine. In 2001, the teenage message was transmitted towards 6 sun-like stars. Various proposals and projects have continued to explore the idea of active messaging to extraterrestrial intelligence, known by the acronym METI. There's debate about whether this is wise. Some scientists argue that we should be quiet, that broadcasting our presence before we understand what might be out there is reckless. Others counter that we're already visible through our inadvertent signals, so deliberate messages make little difference. And still others believe that contact, if it ever happens, is more likely to be beneficial than harmful, that advanced civilizations capable of receiving our signals would likely be peaceful, or at least indifferent. But regardless of the debate, the messages have been sent. They're out there now, travelling, carrying information about who we are, what we look like, where we live, and what we understand about the universe. The Arecibo message is currently about 50 light-years from Earth, having passed dozens of stars on its journey toward M13. The Cosmic Call messages are reaching their target stars around now, give or take a few years. The teenage message is similarly in transit. These are human voices, essentially. Not literal voices, but representations of human thought and creativity and hope. Encoded in electromagnetic radiation, yes, technical and abstract. But at their core, they're an attempt to say, hello, we're here, we exist. We wonder if you do too. And unlike our radio broadcasts and television signals, which were never intended for interstellar audiences and degrade into noise over distance, these deliberate messages were designed to be detectable. They were transmitted with high power, on frequencies chosen for maximum propagation, with encoding designed to be self-explanatory even to someone with no prior knowledge of human language or culture. They're clearer, more intentional, more likely to be recognised as artificial if anyone happens to intercept them. So when we ask whether our signals could have attracted something, we have to include these deliberate transmissions in the accounting. Not just the accidental leakage of radio and TV and radar, but the intentional broadcasts. The moments when humanity collectively decided to speak, even knowing the message would take millennia to arrive, and the response, if any, would take millennia more to return. Those signals are part of our cosmic footprint too, perhaps the clearest part. The part where we consciously chose to be visible, to be heard, to reach out into the dark and say, if anyone's listening, we're here. While electromagnetic signals are fast, travelling at the speed of light, there's something to be said for the physical, the tangible, a message you can hold, information encoded not in waves but in matter. Something that could last not just years but eons, surviving the fall of civilizations and the death of stars. On September 5th, 1977, NASA launched Voyager 1. 2 weeks earlier, on August 20th, they had launched Voyager 2. Identical spacecraft built to explore the outer solar system in a rare alignment of planets that occurs only once every 176 years. Jupiter, Saturn, Uranus, Neptune, all positioned such that a single spacecraft could visit them in sequence, using each planet's gravity to accelerate toward the next. A grand tour of the outer worlds, but the missions didn't end with planetary exploration. Voyager 1 and 2 were designed from the beginning to eventually leave the solar system entirely, becoming the first human-made objects to enter interstellar space. They would travel forever, or until time and entropy wore them down to inert metal, drifting through the galaxy long after Earth was gone. And because they would travel forever, because they represented humanity's first physical presence beyond the sun's domain, NASA decided they should carry a message. Not an electronic signal, but something physical. Something that could be found and understood by anyone who encountered the spacecraft millions of years in the future. They attached golden records to each Voyager. Literally golden, 12-inch gold-plated copper discs like phonograph records, protected by aluminum covers. The covers were engraved with instructions for playing the records, illustrated with simple diagrams showing how to mount the record on a turntable, the proper speed, and how to convert the grooves into audio and images. The instructions assumed the finder had some understanding of physics and mathematics, but made no assumptions about language or culture. They used universal constants like the hyperfine transition of hydrogen to establish units of measurement. They showed binary notation. They provided enough information that any technological civilization should be able to decode the contents, and the contents were extraordinary, a portrait of humanity. An audio-visual encyclopedia of what we are and what we've achieved and what we find beautiful. The records contain 115 images, encoded as audio signals that can be reconstructed into pictures. Photographs of Earth from space, showing the blue marble against black void. Diagrams of our solar system, our place in the galaxy, the structure of DNA. Images of human anatomy, showing how we're put together. Pictures of landscapes, forests, deserts, oceans, mountains. Images of cities and architecture and technology, showing what we've built. Images of humans themselves in various stages of life. A fetus, a mother nursing a child, children playing, couples dancing, old age, an attempt to show the arc of human life from beginning to end. There are greetings in 55 languages, from ancient Sumerian to modern Mandarin. Short phrases, each saying essentially, quote 5, quote 6, quote 7. a way of showing that we're diverse, that we speak in many tongues, but that we can come together to say something simple and universal. There's printed information, a message from President Jimmy Carter and UN Secretary General Kurt Waldheim, extending peaceful greetings from Earth to any finder. And most remarkably, there's music. 90 minutes of music from around the world and across time. Bach's Brandenburg Concerto and Beethoven's String Quartet. Chuck Berry's Sachin quote. Traditional music from Java, Peru, India, Japan, Azerbaijani bagpipes, Australian Aboriginal songs, Louis Armstrong, a Navajo chant, Bulgarian folk, Georgian chorus. Music chosen not because it was popular or commercial, but because it represented the breadth of human culture and emotion. Music that could theoretically be understood by any being that perceives sound and rhythm, even if they don't share our biology or our history. There are also natural sounds. Wind, rain, thunder, ocean waves, birds, whales, elephants, the sounds of Earth itself, the living world we emerged from, and there are human sounds beyond music, laughter, footsteps, a kiss, the sound of a mother and child, heartbeat, pulsar signals, nature's own rhythm, included to show that we've learned to listen to the cosmos. The whole package was curated by a team led by Carl Sagan, designed to represent Earth and humanity as completely as possible within the constraints of the technology and the limited space on a 12-inch disc. And now those records are travelling. Voyager 1, having visited Jupiter and Saturn, headed upward and outward from the plane of the solar system. In 2012, it crossed the heliopause, the boundary where the solar wind gives way to the interstellar medium. It's now more than 15 billion miles from Earth, the most distant human-made object, still transmitting a faint signal back to Earth through the deep space network. Voyager 2, having visited all four gas giants, Jupiter, Saturn, Uranus, and Neptune, took a different path, heading downward and outward. It entered interstellar space in 2018. Both spacecraft are now in the realm between stars, no longer within the sun's protective bubble. Exposed to cosmic rays and the thin gas that fills the spaces between solar systems, their power is fading. The radioisotope thermoelectric generators that provide electricity are decaying, producing less power each year. Within a decade or two, the spacecraft will no longer have enough power to operate their instruments. The transmissions will stop. Communication with Earth will end. But the spacecraft themselves will continue travelling, silent, inert, but intact. Current projections suggest Voyager 1 will pass within about 1.6 light-years of the star Gliese 445 in about 40,000 years. Voyager 2 will come within 1.7 light-years of Ross, 248 in about 40,000 years, and then within 1.65 light-years of Sirius in about 296,000 years. These are not close encounters. The spacecraft won't enter those star systems, but they'll pass through the general neighbourhood, and if any civilization in those systems has the technology to detect and intercept such a small, cold object, they could potentially find it. And if they do, if millions of years from now some being in some distant system discovers a strange artifact drifting through their space, they'll find the golden record. They'll have instructions on how to play it. And they'll hear our music, see our images, learn about our world and our place in it. They'll encounter Bach and Beethoven and Chuck Berry. They'll see photographs of human faces and landscapes and cities. They'll hear greetings in languages long dead. They'll learn the structure of our molecules and the anatomy of our bodies. They'll meet us in a sense, not in person, not in real time. But through this message in a bottle that we cast into the cosmic ocean, hoping that someday, someone, somewhere, might find it and know that they are not alone. That another species once looked up at the stars and wondered, that we existed, that we tried to reach out. It's the longest lasting thing humanity has ever created. Longer than the pyramids, which will erode. Longer than our cities, which will crumble. Longer than our species, which will either evolve into something else or cease to exist. The Voyager spacecraft and their golden records will outlast everything we've made on Earth, everything we are, everything we ever will be. And they carry our story, our music, our voices. Our hope that we are not alone and that someday someone might care enough to listen. So we've been loud, intentionally and accidentally. Radio waves, television signals, radar pulses, nuclear flashes, deliberate messages, physical artifacts drifting into interstellar space, all of it adding up to a cosmic footprint that grows larger and more complex with each passing year. But the question remains, could anyone actually detect us? To answer that, we need to think about what detection would require. We need to consider what technologies might exist, what signatures we produce, and what the limitations of distance and physics impose on observation. Let's start with radio detection, since that's where most of our signal lies. Our strongest transmissions, military radar, air traffic control, certain types of communications, reach power levels that could theoretically be detected across interstellar distances by a sufficiently sensitive receiver. The Arecibo telescope in its prime could have detected a similar telescope anywhere within roughly 1,000 light years if both were pointed at each other and transmitting. That's a sphere of space containing hundreds of millions of stars. Our more routine broadcasts, AM and FM radio, television, are weaker but still detectable within perhaps 50 to 100 light years with advanced enough technology. The key phrase is advanced enough technology. What we can do today represents the bare minimum. Arecibo was a single 305-metre dish. But imagine an array of thousands of such dishes, spread across a planet or even across a solar system, working together through interferometry to create an effective collecting area thousands of times larger. Imagine signal processing algorithms developed by artificial intelligence over centuries, capable of extracting coherent signals from noise levels we can barely measure. Imagine detectors so sensitive that they can pick up individual photons of radio energy and reconstruct patterns from statistical aggregation over years of observation. This isn't fantasy, it's extrapolation. If our radio telescope technology has improved as much in the last century as it has, what might it look like after 1,000 years? 10,000, 1,000,000. An advanced civilization with that kind of technology could monitor hundreds or thousands of star systems simultaneously, looking for artificial signals. They could identify the characteristic modulation of AM and FM broadcasts. They could recognize the structured timing of television transmissions, the sharp pulses of radar, the distinctive signatures of digital communications. They would know these signals are artificial because natural sources don't produce such patterns. Pulses are regular, yes, but they're far too slow and their spectrum is wrong. Lightning produces radio noise, but it's random, incoherent. The kind of organised, information-carrying signals we produce simply don't occur naturally. But radio detection is only one method. There are others, perhaps more revealing ones. Consider spectroscopy. This is the analysis of light to determine what an object is made of. Different elements and molecules absorb and emit light at specific wavelengths, creating a unique spectral fingerprint. By looking at the light from a star and the light from that star passing through a planet's atmosphere, you can subtract one from the other and see what the atmosphere contains. Earth's atmosphere would reveal itself immediately as unusual. The presence of oxygen at 21% concentration is a strong biosignature. Free oxygen is chemically reactive. It doesn't persist in an atmosphere unless something is continuously producing it. On Earth, that something is photosynthesis. Plants, algae, and certain bacteria split water molecules, release oxygen, and fix carbon. Without life, Earth's oxygen would be gone in a geological eye blink. But our atmosphere contains more than just oxygen. It contains industrial pollutants. Chlorofluorocarbons, CFCs, from refrigerants and aerosols. These molecules don't occur naturally. They're purely synthetic, created in chemical factories, They have distinctive spectral signatures in the infrared. An alien astronomer analysing Earth's atmospheric spectrum would see these molecules and know instantly that something artificial is happening on this planet. Methane is another indicator. Earth's atmosphere has rising methane levels from agriculture, rice paddies, livestock, landfills, nitrogen oxides from combustion, carbon dioxide levels rising faster than any natural process could explain. All of this together creates what's called a technosignature, a sign of technology, a fingerprint of industrial civilization visible across light years. The James Webb Space Telescope, launched in 2021, can analyse the atmospheres of exoplanets dozens of light years away. It's designed to look for biosignatures, oxygen, methane, water vapour, signs that life might exist on distant worlds. But it can also, in principle, detect technosignatures. If there's a planet out there with industrial pollution, if there's a civilization that's reached a similar technological level to ours, Webb might find it. Now imagine a civilization with an instrument not just as capable as Webb, but far more advanced. Webb is a 6.5 metre mirror. Imagine a 65 metre mirror, or a 650 metre mirror, or an array of mirrors spread across a solar system, combining their light to create effective apertures measured in astronomical units. With that kind of instrument, Earth would be easy to study. They could resolve features on our surface. They could watch the day-night cycle and notice something unusual. The night side glows, not just with the dim light of lava or lightning, but with structured, concentrated points of light. Cities, streets, highways, stadiums, an unmistakable pattern of artificial illumination that no natural process produces. They could measure our planet's albedo, its reflectivity, and notice variations that correspond to seasons and weather, yes, but also to large-scale agriculture and deforestation and urban expansion. They could watch the polar ice caps shrink. They could detect the heat signature of our civilization, the waste heat from power generation and industry and transportation, slightly warmer than a natural planet should be. They could observe our orbital space and see something strange. Thousands of artificial satellites in carefully arranged orbits, tumbling debris from collisions and old rocket stages, communication satellites in geostationary orbit, hovering over fixed points on our equator. GPS satellites in their distinctive medium-Earth orbits, space stations, the International Space Station making regular passes, soon perhaps lunar bases and Mars colonies. All of this creates an artificial constellation around Earth, a shell of metal and plastic and electronics that no natural process would produce. And if they watched carefully, if they analysed the light reflecting off these objects, they could determine what they're made of. Aluminum, titanium, silicon, materials processed and shaped and launched into space by technology. There's also the neutrino signature. Nuclear reactors produce neutrinos, ghostly particles that barely interact with matter in vast quantities. Earth's nuclear power plants release neutrinos continuously, far above natural background levels. An advanced civilization with neutrino detectors could potentially identify this and recognize it as artificial. And if they had gravitational wave detectors, sensitive enough to pick up minute distortions in space-time, they might even detect our largest structures. Not individual buildings, but perhaps the collective mass of our cities, distributed in ways that natural geology wouldn't produce. Or the regular repeated patterns of satellite orbits, creating subtle gravitational signatures. The point is this: we're not just making radio noise, we're changing our planet in ways that are visible across interstellar distances to anyone with the technology to look closely. We're altering our atmosphere's chemistry, we're lighting up our night side, we're surrounding ourselves with artificial satellites. We're producing waste heat and neutrinos and structured patterns of land use. We've become detectable in multiple ways, through multiple methods, across multiple wavelengths and types of radiation. And the longer we continue our technological development, the more obvious we become. a civilization watching from 50 light-years away with technology even moderately better than ours would have no trouble identifying Earth as inhabited by intelligent technological life. They wouldn't need to guess or speculate. They would know. The evidence would be clear, undeniable, written across our planet's spectrum and geometry and emissions. And if they wanted to look even closer, if they wanted to send a probe or a message or even just pay more attention, they could. They would know exactly where we are, what we're made of, and roughly what level of technology we've achieved. Whether any such civilization exists is of course unknown. The universe might be full of them, or we might be alone, the only technological species in a galaxy of simple life and barren rocks. We don't know, but if they exist, and if they've been watching, then they know about us. Our signals reached them years or decades or centuries ago. Our light passed through their telescopes. Our industrial signature appeared in their spectroscopic data. Our artificial lights drew their attention. And if that's true, if someone out there noticed us, then the question becomes, what might they do about it? Would they watch in silence, send a message back, or perhaps send something more tangible, something we might one day detect approaching from the direction of their star? Something perhaps like an interstellar visitor named 3I/ATLAS, which brings us back to the comet, to the visitor that appeared in our telescopes in April 2024, to 3I/ATLAS, and the curious question of timing. Interstellar objects aren't rare, we're learning. They're probably quite common, actually. Oumuamua in 2017, 2I/Borisov in 2019, now 3I/Atlas in 2024. 3 confirmed in 7 years, and these are only the ones we've detected. Our survey telescopes, while improving, still miss most of what passes through. For every interstellar object we spot, dozens or hundreds probably slip by unnoticed, too faint or too fast or just pointed in the wrong direction when our cameras were looking. So the arrival of 3I/ATLAS itself isn't surprising. These things happen. The galaxy is full of debris, comets and asteroids ejected from their birth systems by gravitational interactions, wandering between stars, occasionally encountering another solar system by chance. But the timing, that's what's interesting. Let's do some math. Calm, simple math. Nothing alarming, just an exercise in thinking about distances and dates. 3I/ATLAS is travelling at roughly 30 to 50 kilometres per second. Let's use 40 kilometres per second as a middle estimate. That's about 0.000133 times the speed of light. Slow by cosmic standards, but typical for objects drifting through the galaxy. At that speed, how long would it take to travel from a nearby star to our solar system? Alpha Centauri, our nearest neighbour, is 4.3 light-years away. At 0.000133 times the speed of light, you'd cover that distance in about 32,000 years. A star 25 light-years away would take about 190,000 years to reach. A star 50 light-years away, about 375,000 years. A star 100 light-years away, 750,000 years. These are long time scales, longer than human civilization, longer than our species has existed in its current form, but not long compared to the age of the galaxy, not long compared to the timescales on which stars and planetary systems evolve. Now, let's think about our electromagnetic bubble. We've been broadcasting for about 100 years. Those signals have reached stars out to about 100 light-years, further technically, but we can hard to detect beyond that range. If 3I/ATLAS came from a star 25 light-years away, and if it left that star around the year 1834 to 190,000 years of travel at 40 kilometres per second, then no, our signals couldn't have triggered its departure. We weren't making any electromagnetic noise in 1834. We were barely into the Industrial Revolution, and radio was decades away from invention. But what if it came from closer? What if 3I/ATLAS was accelerated somehow? What if the physics aren't quite what we assume? Here's where speculation begins. Let's be very clear. What follows is speculation, not established science. It's exploring possibilities, not stating facts. But it's worth thinking through, calmly and carefully. Suppose 3I/ATLAS didn't travel 25 light-years at a natural drift. Suppose it came from closer, say 10 light-years. At 40 kilometers per second, that's about 75,000 years of travel. Still long before our radio age. But suppose it was launched more recently and travelled faster. Not naturally, but accelerated. This is where we enter the realm of what's technologically possible for advanced civilizations rather than what natural processes produce. If a civilization 25 light-years away detected our radio signals, which would have reached them about 75 years ago if they're currently 25 light-years distant, and if they decided to send something in response, and if they had the technology to accelerate an object to, say, 0.01 times the speed of light, at that speed, the object would reach us in about 2,500 years from launch. Too slow. Our signals have only been travelling for 100 years, but at 0.1 times the speed of light, 10% of light speed, which is extraordinarily fast but perhaps achievable for a civilization with advanced propulsion technology, an object could cover 25 light-years in 250 years. Our strongest signals date from the 1940s and 50s. Those signals reached 25 light-years out around 65 to 75 years ago. If something was launched in response and travelled at 10% light speed, it wouldn't arrive for another 175 years or so. So that doesn't work either. Unless, and here's where it gets truly speculative, what if the object didn't need to travel the full distance? What if there was already something closer, waiting? A probe or station positioned within a few light-years of many star systems, monitoring, watching for signs of technological development. If such a probe existed, say, 1 light-year from our solar system, and if it detected our signals when they reached it, around 100 years ago, and if it then launched something toward us at 10% light speed, that object would arrive in about 10 years, around 2014 or so. But 3I/ATLAS was discovered in 2024 and will reach perihelion in 2025, so the timeline is still off, unless the probe was closer, or unless it took time to prepare the object, or unless it launched something that took a slower, more complex trajectory, or unless we're completely wrong about the distances and speeds involved. The point of this exercise isn't to prove anything. It's to show that the math is complicated. There are scenarios, however unlikely, where the timing could work, where our signals could have been detected and where something could have been sent in response, arriving approximately now. But, and this is crucial, all of those scenarios require assumptions we have no evidence for. They require advanced technology that we've never observed. They require motivations and capabilities we can only imagine. They require coincidences and precision that strain credibility. The far simpler explanation, the one that requires no extraordinary assumptions, is that 3I/ATLAS is exactly what it appears to be. A natural comet, ejected from another star system by ordinary gravitational interactions, that has been drifting through the galaxy for hundreds of thousands of years and happened to pass through our solar system during the brief window when we have telescopes capable of detecting it. Correlation is not causation. Just because two things happen around the same time doesn't mean one caused the other. The fact that we've been broadcasting radio signals for a century and an interstellar object arrives during that century could be pure coincidence. In fact, given that we're detecting interstellar objects more frequently now simply because our telescopes have improved, it probably is coincidence. But the timing does make you think. It makes you wonder. Not with alarm or certainty, but with that gentle curiosity that drives scientific inquiry. What if? Could it be? How would we know? And the honest answer is, we probably couldn't know, not for certain. Not without more data than we currently have. We'd need to determine 3I/ATLAS's exact origin point, which is difficult because interstellar trajectories degrade over time, and we can't track backward with perfect accuracy. We'd need to detect anomalies in its behaviour, course corrections, unusual accelerations, anything that couldn't be explained by natural outgassing and gravitational influences. We'd need to analyse its composition in detail, looking for materials or structures that couldn't form naturally. So far, we haven't found any of that. 3I/ATLAS behaves like a comet. It looks like a comet. Its composition, while unusual, isn't impossible for a natural object. Its trajectory follows gravitational laws. There's no evidence of artificial nature or deliberate navigation, which means the most likely explanation remains the simplest. It's a comet. It's natural. Its arrival during our radio age is interesting timing, but ultimately coincidental. Still, the question lingers. In the back of your mind, quiet and persistent, what if? There's another piece to this puzzle, not just when, but where from. When astronomers calculate the trajectory of an interstellar object, they can trace it backward through space, plotting where it came from before gravity from our sun started bending its path. It's not perfect. There are uncertainties, small errors that compound over distance, but it gives a general direction, a region of sky, a part of the galaxy. For 3I/ATLAS, that backward trace points toward the thick disk of the Milky Way. This is a region populated by older stars, formed early in our galaxy's history, orbiting in paths that are more random and less organised than the thin disk where our sun resides. It's a broad area containing thousands of stars within the likely distance range. Without knowing exactly how far 3I/ATLAS travelled, or how long it's been journeying, we can't pinpoint a specific origin. We can only say, somewhere in that general direction, at some distance between perhaps 25 and 100 light years, possibly more. But we can look at what stars lie in that direction. What systems might be candidates for the comet's home? And we can ask, are any of them within our electromagnetic bubble? Could any of them have detected us? Within 100 light years of Earth, in the general direction 3I/ATLAS came from, there are several thousand stars. Most are red dwarfs, small and cool and faint. Some are sun-like yellow stars. A few are larger, brighter. Younger stars still in their prime. Do any of them have planets? Almost certainly. Every star we've examined closely seems to have planets. The Kepler mission and other exoplanet surveys have shown that planetary systems are the rule, not the exception. Most stars have at least one planet. Many have several. Are any of those planets habitable? That's harder to say. We don't have detailed information on most systems in that region. They're too far away for us to detect Earth-sized planets directly. We can estimate, based on statistical models, that a certain percentage probably have rocky planets in their habitable zones, regions where temperatures allow liquid water to exist. But quote 10 doesn't mean inhabited. Still, the possibility exists. Among those thousands of stars, statistics suggest at least a few might have Earth-like worlds. And if even one of those worlds developed intelligent technological life, and if that life reached a level of capability similar to or exceeding ours, and if they were looking outward, monitoring their cosmic neighbourhood for signs of other civilizations, they might have noticed us, detected our radio signals when they arrived, identified Earth as a source of artificial electromagnetic radiation, recognized the techno-signatures in our atmosphere, seen our lights on the night side of our planet, and having noticed us, what might they have done? Option 1. Nothing. Just observe, record the data, note that another civilization has emerged, file it away with whatever other civilizations they might have already found, move on. Option 2. Send a message. 2. A radio signal back toward Earth, encoded to be recognizable as artificial, carrying information. Hello, we received your broadcast, we're here too. Such a message would take decades to arrive, even travelling at light speed. We haven't received anything like that. at least nothing we've recognised. Option 3. Send a probe, a physical object, something that could observe us more closely, gather more detailed data, perhaps even attempt direct contact when it arrives. If 3I/ATLAS was such a probe, what would we expect to see? Well, it would need to look natural, at least superficially. You wouldn't send a shiny metallic spacecraft blazing across the solar system with obvious artificial features. That would be crude, alarming. Better to camouflage it. Make it look like a comet, cover it in ice and dust, let it out gas naturally, give it the appearance of something ordinary so it doesn't trigger panic or defensive responses. It would approach the inner solar system slowly, carefully. Not too close to Earth to be threatening, but close enough to observe, perhaps swinging by the sun to use solar radiation for power or data transmission back home. It wouldn't make contact immediately. It would watch, gather data on our level of development, our social organisation, our technological capabilities, assess whether we're ready for contact or if we need more time to mature, and its trajectory would be carefully planned. Not a random flyby, but a deliberate path that maximises observational opportunities while minimising detection as anything unusual. Here's the problem. Nothing about 3I/ATLAS suggests any of this. Its trajectory is consistent with natural gravitational motion. Its composition, while unusual, is explainable by natural processes. It shows no signs of powered flight, no course corrections, no accelerations that can't be explained by outgassing. It's not emitting any signals we can detect beyond the natural infrared glow of warming ice. It behaves exactly like a comet should behave. So either it's a spectacularly well-disguised probe, indistinguishable from a natural object even under close examination, or it's simply what it appears to be, a comet. Occam's razor, the principle that the simplest explanation is usually correct, strongly favours the latter. A natural comet requires no extraordinary assumptions. A disguised probe requires advanced technology, specific motivations, precise timing, and a whole chain of improbable decisions by a civilization we've never confirmed exists. But there's still that direction, that alignment, the fact that it came from a region of space our signals have reached, a region where, statistically, intelligent life could exist. It doesn't prove anything. Correlation isn't causation. Coincidences happen. The universe is full of alignments that mean nothing, patterns that our pattern-seeking brains want to interpret as significant, but are actually just the way things randomly fell. And yet it's hard not to wonder. When you look up at the night sky, toward the constellation where 3I/ATLAS originated, knowing that our radio signals have washed over those stars, knowing that anyone there could have heard us, it's hard not to wonder if someone did, if something was sent in response. If this ancient ice, this wandering visitor, carries more significance than we yet understand, or if we're simply seeing what we want to see, finding meaning in randomness, hoping, despite all evidence and probability, that we're not alone. Both possibilities are humbling. One suggests the universe is more connected and responsive than we thought. The other suggests we're projecting our loneliness onto indifferent cosmic debris. Either way, 3I/ATLAS continues its journey, approaching the sun, warming, releasing gas and dust, following the ancient laws of gravity and thermodynamics, saying nothing, revealing nothing beyond what it appears to be, and we watch, we measure, we speculate, and we wait to see if anything else emerges from the direction it came from, anything that might confirm or deny our quiet hopes that our signals were heard, before we go too far down the path of speculation. It's worth stepping back and considering the more mundane explanations, the ones that don't require advanced civilizations or interstellar probes, the ones grounded entirely in ordinary physics and natural processes, because the truth is, everything about 3I/ATLAS can be explained without invoking intelligence or intent, easily, convincingly. Let's start with how interstellar objects come to exist in the first place. when a planetary system forms, not all the material ends up in planets. There's a lot of leftover debris, small bodies, planetesimals, chunks of rock and ice that didn't quite accumulate into full planets. These objects orbit the parent star in various regions. In our solar system, they're concentrated in the asteroid belt between Mars and Jupiter, the Kuiper belt beyond Neptune, and the distant Oort cloud that may extend a light year or more from the Sun. These populations are stable for the most part. Objects orbit for billions of years without significant disturbance. But occasionally, something happens. A close encounter with a planet, a passing star that tugs gravitationally on the outer edge of the system, a collision that changes an object's trajectory. When this happens, an object can be ejected, thrown out of its home system entirely, with enough velocity to escape the star's gravity. It becomes an interstellar wanderer, no longer bound to any star, drifting through the galaxy at whatever speed the ejection gave it. This process is probably common. Every planetary system likely ejects material over its lifetime. The younger the system, the more violent and frequent the ejections as planets migrate and orbits settle. Older systems are calmer but still occasionally eject objects through random gravitational interactions. So the galaxy should be full of these wanderers, trillions upon trillions of them. Comets, asteroids, planetesimals of all sizes, drifting between stars at typical velocities of 20 to 50 kilometers per second. Most are small and dark and completely undetectable unless they happen to pass very close to a star or planet. Our solar system, moving through the galaxy at about 230 kilometers per second in its orbit around the galactic centre, encounters these wanderers regularly. Most pass far from the Sun, never coming close enough to be noticed, but occasionally one drifts through the inner system where our telescopes can spot it. Oumuamua was the first we detected. Not the first to pass through, certainly not, but the first we had the technology and attentiveness to notice. 2I/Borisov was the second. 3I/ATLAS is the third. The fact that we're detecting them now in the 2010s and 2020s isn't because they started arriving now. It's because we started being able to detect them now. Our telescopes have improved. Our survey programs scan more of the sky more frequently. Our automated detection algorithms have gotten better at spotting faint moving objects against the background of stars. In another decade, we'll probably be detecting several interstellar objects per year. In a century, perhaps dozens. Not because more are arriving, but because we're getting better at seeing what was always there. This is known as an observational bias, the phenomenon where you notice things more when you're looking for them, or when you have better tools. It doesn't mean the things suddenly started happening, just that you're finally equipped to see them. So 3I/ATLAS, arriving during our radio age, could simply be a coincidence of detection capability. We happen to be in the era where we can spot these objects and also the era where we've been broadcasting. The overlap is not causal, it's just timing. As for the unusual composition, that high carbon dioxide to water ratio, that's interesting but not impossible to explain naturally. Comets form in the outer regions of planetary systems where temperatures are low enough for volatile compounds to freeze. But different compounds freeze at different temperatures. Water ice forms at relatively high temperatures. Cosmically speaking, around 150 Kelvin in the low-pressure environment of space. Carbon dioxide freezes at about 80 Kelvin. Carbon monoxide at 25 Kelvin. If 3I/ATLAS formed in a particularly cold region of its home system, farther out than most comets, it might have accumulated more of the ultra-volatile ices like CO2 and CO. Or if it's been wandering for a very long time, it might have lost most of its water ice through previous encounters with stars, leaving behind the less volatile carbon dioxide. There are also compositional variations based on the chemistry of the protoplanetary disk. A star system with more carbon relative to oxygen would produce comets with different ice ratios than a system like ours. This is perfectly natural. just reflecting the original composition of the molecular cloud that formed the star. The early outgassing at 4.4 astronomical units is also explainable. If the comet contains a high proportion of carbon monoxide or other very volatile ices, those would start sublimating at greater distances from the Sun than water ice. The early activity doesn't require anything artificial, just a particular composition that's less common but entirely plausible. The trajectory itself is hyperbolic, yes, meaning it's not bound to our Sun, but that's expected for an interstellar object. It came from elsewhere, and it's leaving. The specific path it's following is consistent with gravitational dynamics. An object approaching from interstellar space at a certain velocity from a certain direction would naturally fall toward the Sun, swing around it picking up speed, and head back out at a different angle. The math works. No course corrections needed. So here's the alternative explanation, the boring but scientifically sound one. 3I/ATLAS is a chunk of ice and rock that formed around another star, probably between 25 and 100 light-years away, sometime in the past few billion years. Through natural gravitational interactions, possibly an encounter with a large planet or a passing star, it was ejected from its home system. It's been drifting through the galaxy ever since, hundreds of thousands or millions of years, covering vast distances at a few dozen kilometers per second. By chance, its trajectory happened to intersect our solar system. This isn't rare on galactic timescales. With trillions of these objects wandering between stars, encounters are inevitable. It approached our Sun, began to warm and outgas as its volatile ices sublimated, and became bright enough for our telescopes to detect. We spotted it in April 2024 because our survey technology has reached the point where we can detect such objects. We studied it, measured its properties, and found it unusual in some ways, but not impossibly so. It will reach perihelion in January 2025, swing around the Sun, and head back into interstellar space, where it will continue wandering for another few million years, until perhaps encountering another star system. No intelligence required, no deliberate dispatch, no response to our signals, just natural processes, random motion, and the statistical certainty that if you wait long enough and watch carefully enough, you'll see interstellar debris passing through. This explanation requires no extraordinary assumptions. It aligns with everything we know about planetary formation, gravitational dynamics, and the frequency of interstellar objects. It's consistent with the observed properties of 3I/ATLAS. It's the scientific consensus, the explanation that professional astronomers accept. And it's probably correct. Probably. But, and this is where science remains beautifully open to possibility, probably isn't certainly. The natural explanation fits. It works. It's elegant and sufficient. But it doesn't preclude other explanations, however unlikely. It doesn't close the door on wondering, on asking quote 13 even as we acknowledge quote 14, because that's what science does. It follows the evidence where it leads, favouring simplicity and natural explanations, but remaining open to revision if new data suggests something different. It doesn't claim absolute certainty. It builds models, tests them, refines them, and sometimes, rarely, those models reveal that the universe is stranger than the simple explanation suggested. Most of the time, the simple explanation is right. Most of the time, the natural answer is the correct one. Most of the time, a comet is just a comet, but not always. And that small uncertainty, that gap between quote 15 and quote 16 is where wonder lives. Let's enter that gap. That space of unlikely but not impossible. Let's explore calmly and carefully what it might mean if 3I/ATLAS were something more than a random visitor. Not to convince ourselves that it is, just to think through what that scenario would look like, what it would imply, how we might recognize it, and what it would say about our place in the universe. Imagine for a moment that a civilization exists around a star 40 or 50 light-years from Earth. A technological civilization, perhaps millions of years old. with capabilities far exceeding ours. They have long-range observatories capable of detecting the faintest electromagnetic signals across interstellar distances. They monitor their cosmic neighbourhood not out of paranoia, but out of curiosity, the same impulse that drives our own SETI programs. In the 1960s and 1970s, our strongest radio signals reach their system. Radar pulses from military installations, the nuclear flash of atmospheric tests, television broadcasts, the unmistakable signature of technological activity. Their instruments detected it. Their analysts confirmed it. Another civilization had emerged, young, loud, energetic, approximately at the level where they understand atomic energy and basic spaceflight. Exactly the stage where civilizations either mature into cosmic responsibility or destroy themselves. They faced a decision. Contact. Direct communication would be possible. Send a radio message back. But that would take decades to arrive, and then decades more for a reply. The conversation would span centuries, and the receiving civilization, us, would be undergoing rapid technological and social change during that time. What we are now might be unrecognizable by the time the first exchange completed, or they could send a probe, a physical emissary, something capable of autonomous observation, of gathering detailed data about this new civilization without the need for light-speed communication delays, something that could watch us up close and report back. But you can't just launch a spacecraft at another star and expect it to arrive quickly. Even with advanced propulsion, interstellar distances are vast. At 10% of light speed, extraordinarily fast by any current standard, covering 50 light-years takes 500 years, and accelerating anything to that speed requires enormous energy. Unless you don't need to send it from your home star, unless you've already placed observational platforms throughout your local neighbourhood, automated stations in the dark space between stars, positioned strategically to watch multiple systems, waiting for signs of technological development. If such a station existed within a few light-years of Earth, it could have detected our signals much sooner. Perhaps in the 1950s or 60s, when our strongest transmissions began. And if it had the capability to dispatch a probe, perhaps something it manufactured from local resources, cometary ice and interstellar dust, assembled into a functional observational platform, it could have launched something toward us that would arrive within decades rather than centuries. Such a probe would need to look natural. It would need to pass through our system without triggering defensive responses or mass panic. The best camouflage would be to disguise itself as exactly what we'd expect to see. A comet from interstellar space. Cover it in ice. Let it outgas naturally as it approaches the sun. Give it the composition of a comet, the trajectory of a comet, the behaviour of a comet. Make it virtually indistinguishable from the natural objects that occasionally pass through. But inside, perhaps there's more. Instruments, sensors, maybe a power source that wakes up as it nears the sun and begins to warm. Maybe communication equipment that will transmit data back to its origin once it's gathered enough information about us. Or maybe it's even simpler. Maybe it's just a marker, a passive object placed in our path, designed to be noticed, to be studied, to contain information encoded in its structure or composition. A message we'd have to work to decode, proving our technological capability in the process. These scenarios sound like science fiction. They require technologies we don't possess, and motivations we can only imagine. But they're not physically impossible. Nothing in known physics prevents an advanced civilization from building automated probes or placing monitoring stations between stars. It's just engineering at a scale we haven't achieved yet. And if such a thing were here, how would we know? The honest answer is, we probably wouldn't. Not unless it wanted us to know. Not unless it deviated from natural behaviour in ways our instruments could detect. We'd look for anomalies, course corrections that couldn't be explained by outgassing or gravity, accelerations inconsistent with natural forces, signals in unexpected frequencies, materials in the wrong proportions or wrong configurations, structures too regular to be natural. So far, We've found none of that in 3I/ATLAS. It looks natural, acts natural, responds to heat and gravity as a comet should. There's no evidence of artificiality, which means either it's genuinely natural or it's so well disguised that we can't tell the difference with current technology. Both possibilities lead to the same practical conclusion. We should treat it as natural and continue observing to see if anything unusual emerges. But let's extend the thought experiment. Suppose it is a probe. Suppose we are being observed. What would that mean? First, it would mean we're not alone. That's profound. The universe contains at least one other technological civilization, advanced enough to detect us and dispatch an interstellar probe. The cosmic loneliness that has defined human existence since we first looked up at the stars would end. We'd have proof that intelligence, technology, civilization, these aren't unique to Earth. They emerge elsewhere, perhaps commonly. Second, it would mean we've been noticed. Our electromagnetic signals worked. Our unintentional advertisement of our presence succeeded. We're visible, and visibility has consequences. We don't know if those consequences are positive or negative. Science fiction often assumes conflict, invasions, resource competition, existential threat. But there's no particular reason to assume hostility. A civilization capable of interstellar travel has presumably solved its resource problems. They wouldn't need our water or metals or living space. They could get those anywhere. More likely, they'd be curious, interested in studying another intelligence, understanding how we developed, what we're like, what we might contribute to a larger galactic community, if such a thing exists. Or they might be cautious, watching to see if we're stable enough, mature enough, wise enough to be contacted directly, waiting to see if we survive our adolescence as a technological species, if we avoid destroying ourselves with our own inventions, if we develop the philosophical and ethical frameworks necessary to handle the knowledge that we're not alone. And third, it would change how we see ourselves. We'd no longer be the only intelligent species we know. We'd be one among many, or at least one among two. That shift in perspective from cosmic centrality to cosmic membership would reshape philosophy, religion, politics, culture. Everything about how we think about our place and purpose would change. But all of this remains hypothetical, imagined, based on scenarios that fit the facts but aren't required by them. The most likely explanation, as we've said, is natural. 3I/ATLAS is probably just a comet. Its arrival during our loud century is probably coincidence. The timing, the direction, the composition, all explainable by ordinary processes. But the possibility lingers, the what if, the maybe, the quiet recognition that we can't be absolutely certain, that the universe might surprise us, that our signals might have been heard and answered in a way we're only now beginning to recognize. And whether it's true or not, the exercise of thinking it through has value, because it forces us to consider what we are in cosmic terms, to think about what we've broadcast and what it might mean, to recognize that our presence, our noise, our existence, these have consequences that extend beyond our planet, beyond our solar system, into the vast dark between stars. We've made ourselves known. We've reached out. And now, whenever an object arrives from the direction of that reaching, we can't help but wonder, is this a response? Is someone reaching back? Whether 3I/ATLAS is natural or artificial, whether our signals attracted it or not, one thing remains undeniably true. We're no longer cosmically invisible. We have left our mark on the universe in ways that extend far beyond Earth's surface. Let's take a moment to consider the full scope of humanity's cosmic footprint. Not just the radio signals we've discussed, but everything. The complete picture of how we've changed our immediate environment in ways that might be detectable from afar. Start with Earth's orbit. A century ago, it was empty except for the occasional meteor and the natural zodiacal dust cloud left by comets. Now it's full of our constructions. The United States Space Surveillance Network tracks more than 27,000 objects larger than 10 centimetres. These include active satellites, approximately 10,000 at last count, with numbers growing rapidly as companies like SpaceX launch mega constellations for global internet coverage. But the tracked objects are just what's large enough to monitor. There are hundreds of thousands of smaller pieces, fragments from collisions, paint flecks, bits of metal and plastic shed from aging spacecraft, frozen droplets of coolant and propellant, all of it orbiting Earth at thousands of miles per hour, creating a shell of artificial debris around our planet. This shell is visible, not to the naked eye from interstellar distances, but to instruments sensitive enough to detect reflected sunlight from small objects. An advanced civilization observing our system would see an unusual concentration of reflective material in specific orbital zones. Geostationary orbit at 35,786 kilometers altitude would show a ring of satellites. Low Earth orbit would show a swarm of objects in carefully aligned paths. This doesn't happen naturally. Rocks don't arrange themselves in orbital shells around planets. Dust doesn't maintain specific altitudes and inclinations. The pattern is clearly artificial, a signature of spaceflight capability. And we're expanding that footprint. The International Space Station maintains a permanent human presence in low orbit. China has its own space station. Plans exist for commercial stations, lunar gateways, and eventually permanent bases on the Moon and Mars. Within a few decades, human activity in space might include mining operations on asteroids, fuel depots in strategic orbits, manufacturing facilities taking advantage of microgravity, and infrastructure supporting the colonization of other worlds in our solar system. All of this creates more signatures, more objects in unnatural orbits, more electromagnetic emissions as communication between these outposts increases, more light, not just reflected sunlight but artificial lighting from stations and colonies, visible to anyone watching our planets closely. Mars, if we succeed in establishing a presence there, will develop its own artificial signatures, orbital satellites, surface vehicles, eventually habitats and infrastructure that alter the landscape in detectable ways. If we progress to terraforming, deliberately altering Mars's atmosphere to make it more Earth-like, that would create an unmistakable techno-signature visible across light years. Our energy usage is also detectable. Earth emits more waste heat than a natural planet should. Power plants, vehicles, buildings, industry all convert energy into heat, and that heat radiates into space. The excess is small, a fraction of a percent compared to the natural geothermal and solar heat budget, but it's there, and it has a different spectral signature than natural sources. As our energy consumption grows, and it has grown exponentially since the Industrial Revolution, this heat signature becomes more prominent. Some scientists have proposed that very advanced civilizations might have heat signatures detectable across interstellar distances. Waste heat from massive energy consumption creating infrared excess around their star systems. We're not at that level yet, but we're moving in that direction. There's also our impact on Earth's albedo, its reflectivity. Large-scale agriculture changes how much sunlight the planet reflects. Deforestation alters reflectivity patterns. Urban areas, with their concrete and glass, reflect differently than natural landscapes. These changes are subtle but potentially detectable to careful observers monitoring our planet over decades. The chemical composition of our atmosphere continues to change. Carbon dioxide levels are rising faster than any natural process could explain. Methane from agriculture and industry, nitrogen oxides from combustion, fluorinated gases from refrigeration and industrial processes. All of these create spectral signatures that don't occur naturally. They're techno-signatures, evidence of industrial activity. And then there are the missions we've sent beyond Earth's orbit. Voyager 1 and 2, as we've discussed, are now in interstellar space, but they're not alone. Pioneer 10 and 11 also left the solar system. New Horizons, after its flyby of Pluto, is heading outward on its own escape trajectory. Eventually we'll have a small fleet of human artifacts drifting through the galaxy. Each carries information about us. The pioneers have plaques showing a man and woman, the structure of hydrogen, and our location relative to pulsars. The Voyagers have their golden records with music and images. Even spacecraft without deliberate messages carry information in their construction, materials, design, manufacturing techniques that speak to our technological level. We've also left physical traces on other worlds, footprints on the moon from the Apollo missions protected by the absence of wind and weathering will remain for millions of years, landers and rovers on Mars, probes that crashed into Venus and Jupiter, equipment left on asteroids and comets. These artifacts mark our presence in the solar system in permanent ways. They're time capsules of our technological capability at specific moments in history. And they're discoverable by anyone who might visit these worlds in the future. All of this, the satellites, the heat signature, the atmospheric changes, the physical artifacts, the electromagnetic signals, combines to create a comprehensive picture of a technological civilization in its adolescent phase. We're past the early stages of simple agriculture and basic tools. We've developed industry, spaceflight, atomic energy. We've begun to modify our planet and reach beyond it. We're on the cusp of becoming a multi-planetary species, and all of this is visible, to varying degrees depending on the observer's distance and technological capability, but visible nonetheless. We've announced ourselves not just with radio signals, but with our actions, with what we've built and where we've been and how we've changed our environment. We can't unring this bell. We can't make ourselves invisible again. Short of abandoning all our technology, returning to pre-industrial existence, and waiting for our electromagnetic signals to disperse into undetectable noise, which would take decades at minimum, we're committed to visibility. The question isn't whether we can hide. We can't. The question is how we proceed now that we're known. Or at least now that we're knowable, detectable, findable by anyone looking in our direction with the right tools. Do we continue broadcasting deliberately, sending more messages like Arecibos, actively trying to contact potential civilizations? Do we listen more carefully with our own instruments, searching for responses or signals from others? Do we proceed with our development plans, expanding into the solar system, increasing our visibility further? There's no consensus on these questions. Different groups have different answers, but the baseline fact remains: we're no longer hidden. For better or worse, humanity has become a cosmic presence. Small still, limited to one star system, barely scratching the surface of what's possible, but present, active, visible, and growing more so with each passing year. This growing visibility raises questions that previous generations of humans never had to consider. For most of human history, we were cosmically irrelevant, too primitive to be noticed, too quiet to be heard. What we did on Earth stayed on Earth, but that's no longer true. And now we face a dilemma that philosophers and scientists are still debating. Should we be making noise in the cosmic dark? This is known as the METI debate, messaging to extraterrestrial intelligence. It's the active counterpart to SETI, the search for extraterrestrial intelligence. SETI is passive, listening for signals from others without transmitting ourselves. METI is active, deliberately broadcasting messages designed to be found. The arguments on both sides are worth considering carefully. Those who favour caution, sometimes called the quote 17 camp, make several points. First, we don't know what's out there. The universe could contain friendly, curious civilizations interested in peaceful contact, or it could contain something else, something competitive, something that views emerging civilizations as threats or resources. We simply don't know. In the absence of knowledge, they argue, wisdom suggests caution. Don't advertise your presence until you understand the neighborhood. Don't make yourself a target before you're capable of defending yourself. Wait, watch, listen. Learn what's out there before deciding whether to reveal yourself. This is sometimes called the dark forest hypothesis. based on a concept from science fiction. The idea is that the galaxy might be like a dark forest, where every civilization is a hunter moving quietly through the trees. The first to make noise, the first to reveal their position, might become prey. So everyone stays silent, listening but not speaking, watching but not being seen. It's a paranoid view. But paranoia isn't always wrong. History shows that contact between civilizations at different technological levels often goes badly for the less advanced one. Colonialism, conquest, cultural destruction, these are patterns that appear repeatedly in human history, when more advanced societies encounter less advanced ones. Extrapolating to cosmic scales, the argument goes, why assume aliens would be different? Why assume they'd be benevolent rather than exploitative? Better to stay quiet until we know more. Better to be safe than optimistic. Those who favour active messaging, the secondist quote 18 Neil's camp, counter with several arguments. First, it's too late to hide. We've been broadcasting for a century. Our radio bubble extends 100 light years. Anyone within that radius already knows we're here if they're looking. Staying quiet now doesn't change what we've already revealed. The choice between hiding and revealing was made in 1920 when we started commercial radio. We're past the decision point. Second, the dark forest hypothesis assumes hostility without evidence. Most scenarios of interstellar civilization suggest that by the time a species achieves the technology for interstellar travel or communication, they've solved their resource problems. They have abundant energy, access to materials throughout their solar system, no need to compete for living space. Why would they bother with invasion or exploitation? More likely, they'd be curious, interested in diversity, happy to encounter another mind, another perspective, another way of understanding the universe. Intelligence is probably rare in cosmic terms. Finding another instance of it would be valuable for knowledge, for culture, for the simple relief of knowing you're not alone. Third, contact might be beneficial. An advanced civilization could share knowledge, technology, philosophy. They could help us avoid mistakes they made in their own development. They could provide perspective on problems we're struggling with. Climate change, resource management, social organisation. The potential benefits of contact could far outweigh the risks. And fourth, there's a moral argument. If we stay silent out of fear, we deny potential contact to future generations. We make a choice for all humanity based on our own timidity. Maybe we have the right to make that choice. Or maybe we should be bolder, willing to reach out despite uncertainty, because the possibility of finding others in the cosmos is worth the risk. Both sides have merit. Both raise valid points. There's no clear answer, no consensus. But there's another consideration that sometimes gets overlooked in these debates. We can't actually control our visibility. Yes, we could stop deliberately transmitting. But we can't stop being a technological civilization without abandoning the technologies that define modern life. Our satellites need to communicate. Our power grids emit electromagnetic noise. Our industry produces waste heat and atmospheric changes. Even if we stopped broadcasting entertainment and stopped sending deliberate messages, we'd still be visible to anyone with sensitive enough instruments. The only way to truly hide would be to regress technologically. To abandon electricity, stop using radio, eliminate all our satellites, and return to a pre-industrial state. And even then, the signals we've already sent would continue travelling outward for years to come. So the question isn't really whether to be visible. We are visible. The question is whether to be intentionally communicative, whether to try actively to contact others, or simply to exist and let our existence speak for itself. And that's a more subtle question. It's the difference between walking through the forest quietly but carrying a light versus shouting hello at regular intervals. The light might be spotted by someone looking. The shout ensures you're heard by anyone in range. Both have risks and benefits. Both reveal your presence but in different ways and to different degrees. Most scientists working in the field lean toward a middle path. Continue SETI. Keep listening, Keep searching for signals from others. Don't start massive, continuous broadcast campaigns designed to reach thousands of stars. But don't avoid all active messaging either. Occasional, carefully considered transmissions to specific, promising targets. Messages designed to be informative and non-threatening. Attempts at contact that are thoughtful rather than reckless. And most importantly, make these decisions collectively, not as isolated scientists or national space agencies, but as a species. Because the decision to broadcast affects everyone. It's not something any single group should decide unilaterally. Organisations like the International Academy of Astronautics have proposed protocols for this. Guidelines suggesting that before any major METI transmission, there should be international consultation, scientific review, ethical consideration. No single person or nation should speak for Earth without Earth's permission. Whether those protocols are followed is another question, but the intent is sound. Recognise that our cosmic voice belongs to all of us, and decisions about how to use it should be made collectively. Meanwhile, the debate continues. Papers are published, conferences are held, arguments are made on both sides, and all the while, our signals continue travelling outward, carrying the sound of humanity deeper into the galaxy, whether we meant to send them or not. We've become loud. The question now is whether to become louder or to maintain our current volume, whether to shout deliberately or let our unintentional noise speak for us. And someday, perhaps, we'll receive an answer, a signal from someone who heard us, a message saying hello back, and then we'll know whether our noise brought connection or consequence. Whether our visibility led to contact or caution, whether the universe is friendly or indifferent or something we haven't yet imagined. Until then, we continue, broadcasting, building, expanding our footprint, making ourselves known, and waiting to see what happens next. There's a loneliness at the heart of human existence. We've felt it for as long as we've been capable of looking up at the night sky and wondering what else might be out there. The stars are beautiful, yes. The cosmos is vast and awe-inspiring, but it's also empty in a profound way. We've sent signals, we've listened, we've built sensitive instruments capable of detecting the faintest whispers from across the galaxy. And for a century we've heard nothing, no response, no indication that anyone else is there. This is sometimes called the Great Silence, or the Fermi Paradox, after physicist Enrico Fermi, who famously asked, if the galaxy is old and large, and if planets are common, and life is even moderately likely, there should be many civilizations out there, some far older than us, far more advanced. Where are they? Why haven't we heard from them? Why haven't they visited or at least said hello? The silence is deafening, and it raises uncomfortable possibilities. Maybe we're alone. Maybe life is common, but intelligence is rare. Maybe technological civilizations destroy themselves before they can spread or communicate. Maybe interstellar distances are just too vast and everyone is isolated by the sheer scale of space. Or maybe they're there, but silent, watching without speaking, avoiding contact for reasons we don't understand. Living with this silence, this uncertainty, has shaped human philosophy and psychology in subtle ways. We're simultaneously hopeful and pessimistic. We search while half expecting to find nothing. We broadcast while suspecting no one is listening. But what if that changed? What if we discovered we had been heard? Not contacted directly necessarily. Maybe the contact is subtle. Maybe it's ambiguous. Maybe it's something like 3I/ATLAS, an arrival that could be natural, could be a response, leaves us wondering but not certain. Even that, even the possibility, even the uncertainty, changes things. First, it changes our self-perception. We're no longer the only known intelligence in a dead universe. We're potentially one among many, part of a larger community of minds, even if we haven't met the others yet. This is humbling and elevating simultaneously. Humbling because it means we're not special, not unique, not cosmically central. Everything we've thought and done and built might have parallels elsewhere, accomplished by beings we've never met. Our struggles, our achievements, our history, all of it might be unremarkable on cosmic scales. But it's also elevating because it means we've achieved something significant. Out of the vast indifference of the universe, intelligence emerged here. Consciousness, curiosity, creativity. The drive to understand and explore. If others exist, we share that with them. We're connected by something deeper than biology or chemistry. We're connected by the fact of awakening, by the choice to look outward and ask questions. Second, it changes our responsibility. If we're alone, we can do as we please. We're accountable only to ourselves. But if others exist, if they're watching, if our signals have been heard and perhaps answered, then we're part of something larger. We have an audience. Our actions have witnesses. This might sound constraining, but it could also be motivating. It's easier to be careless with your planet when you think no one else exists to notice or care. It's harder when you imagine other civilizations observing, judging, perhaps hoping you'll grow up and become responsible enough for contact. It's like the difference between thinking you're alone in a dark room versus knowing someone might be watching. Your behavior changes, not because of fear or judgment necessarily, but because of awareness. Because you're conscious of being part of something larger than yourself. Third, it changes our future. If contact is possible, if communication might happen, then the long-term trajectory of human civilization includes an interstellar dimension. We're not just earth-bound primates destined to live and die on one planet. We're potential members of a galactic community. That reframes everything. Political conflicts seem smaller when you imagine explaining them to an alien anthropologist. Religious differences seem less cosmic when you consider that others might have entirely different spiritual frameworks based on different histories and biologies. National boundaries seem arbitrary when you think about them from a perspective that sees Earth as a single, unified world. This doesn't solve our problems. It doesn't make wars stop or inequality disappear or climate change reverse. But it provides a different context for thinking about those problems. A cosmic context. A perspective that might help us see beyond our immediate concerns to longer-term patterns and possibilities. And maybe that's what we need. Not alien intervention, not rescue from outside, but perspective. The knowledge that we're not alone, that our choices matter on scales larger than we imagined, that the universe might be watching to see what we become. There's a concept in psychology called the overview effect. Astronauts who've seen Earth from space describe a shift in consciousness. Seeing the planet as a whole, a fragile blue marble against infinite black, changes how you think about it. National boundaries disappear. The atmosphere looks thin and vulnerable. The interconnectedness of everything becomes obvious, and you feel a profound sense of responsibility to protect it. Perhaps being seen, or believing we might be seen, creates a similar effect. A cosmic overview, a recognition that our local concerns are nested within larger contexts, that our planet is part of a solar system, our solar system part of a galaxy, our galaxy part of a universe that might contain countless other minds looking outward just as we do. This can be terrifying. The loss of cosmic centrality, the recognition of our smallness and fragility, the awareness that we might be judged by standards we don't yet understand. But it can also be beautiful. The terror and beauty are intertwined, two sides of the same realization. We matter enough to be noticed. We're interesting enough to be worth watching. Our story is unfolding in a universe that might care about the outcome. Whether 3i/ATLAS is natural or artificial, whether our signals were heard or not, the fact remains. We've reached the stage of development where these questions are meaningful. We're loud enough to potentially be heard. We're technologically sophisticated enough to send probes to other worlds, to detect visitors from other stars, to begin asking seriously what it means to be part of a cosmic community. We're no longer isolated by ignorance. We know the universe is vast. We know planets are common. We know the chemistry of life operates under universal laws. We know that if it happened here, it could happen elsewhere. And that knowledge, even without confirmation, even without contact, changes us. It changes how we think about ourselves, our planet, our future. It creates a sense of possibility that didn't exist for previous generations. The possibility of connection, of understanding, of finding somewhere in the dark another voice saying hello. We might wait centuries for that hello. It might never come. But the waiting itself is meaningful. The reaching out, the wondering, the hoping despite silence. Because in the end, what it means to be seen, or to believe we might be seen, is to recognize that we're part of something larger, that our existence, our noise, our presence in the universe has significance beyond our planet, that we're not just a random accident on a random rock, but participants in a cosmic story still being written. And whether anyone's reading that story or not, whether anyone noticed our signals or cares that we're here, we're still writing it, still broadcasting, still reaching into the dark, still hoping that somewhere, someone might reach back. Let's bring this back to where we started, to 3I/ATLAS, to the question of whether we triggered anything, to the timing and the direction, and the wonder and the uncertainty. The most honest answer after all this exploration remains what it was at the beginning. We probably didn't trigger anything. 3I/ATLAS is almost certainly a natural comet, ejected from another star system through ordinary gravitational processes, wandering through the galaxy for hundreds of thousands of years, arriving in our solar system by chance during the brief window when we have telescopes to detect it. The timing is interesting, but likely coincidental. The composition is unusual, but explainable. The trajectory is consistent with natural motion. Nothing about it requires artificial origin or deliberate dispatch. We probably didn't trigger it. But, and here's what matters, we could have. The universe we live in, the physics we understand, the technologies that might be possible for civilizations older than us, the detectability of our signals across interstellar distances, all of it allows for the possibility that we've been heard, that someone noticed, that a response might be on its way. We can't prove it didn't happen. We can only say it's unlikely. And there's a profound difference between impossible and unlikely. The unlikely leaves room for wonder, for possibility, for the recognition that the universe might be stranger and more connected than the simple explanation suggests. And whether 3I/ATLAS specifically is natural or artificial, whether our signals have been heard or not, one undeniable fact remains. We reached out, not just with the Arecibo message or the Voyager records, but with every radio broadcast, every television transmission, every radar pulse, every satellite we launched, every light we turned on, every change we made to our atmosphere's chemistry. We made ourselves known. We announced our presence. We sent the universe a message, intentional or not, that said, something intelligent exists here. Something that builds and communicates and wonders and hopes. That message is real. It's travelling outward right now, at this very moment. The signals from the 1920s are 100 plus light years away, passing through star systems we've barely catalogued. The signals from the 1960s are 60 plus light years out. The signals from last year are just leaving the solar system. All of it carrying pieces of us. Music and voices and mathematical patterns and the unmistakable signature of technology. All of it saying to anyone who might intercept it, we're here, we exist. We're trying to understand. We hope you do too. And the physical artifacts, Voyager 1 and 2, Pioneer 10 and 11, New Horizons, they're still travelling, still carrying their messages in physical form, still drifting through space toward distant encounters that might never happen, but might someday mean everything. Those golden records will outlast us. They'll survive long after human civilization has transformed into something unrecognizable or ceased to exist entirely. They'll carry our music and our greetings and our images through the galaxy for billions of years. That's immortality of a sort. Not personal immortality. The individuals who made that music and spoke those greetings are long dead or soon will be. But collective immortality. Species-level immortality. The message survives even when the messengers don't. And there's something beautiful in that. Something hopeful. We didn't know if anyone would hear. We still don't know. Maybe no one ever will. Maybe the messages will drift forever through an empty galaxy, encountering nothing but gas and dust and the occasional lifeless rock. But we sent them anyway. We reached out anyway. We made the effort to communicate, to connect, to say quote 21 into the void despite not knowing if anyone would answer. That says something about us, about what we value, about what we hope for. It says we're not content with isolation. We're not satisfied with the possibility of being alone. We're curious, hopeful, willing to risk looking foolish or being ignored if there's even a chance of making contact. It says we believe communication matters, that understanding matters, that finding others in the cosmos would be worth the effort and the waiting and the uncertainty. It says we're brave enough to be vulnerable. Broadcasting our presence is vulnerability. It's saying quote 22 quote without knowing who or what might respond. It's opening ourselves to observation, to judgment, to possibilities we can't control. But we did it anyway, because the alternative, staying silent, hiding, accepting isolation as permanent, was worse. And even if our signals never reach anyone, even if we're truly alone in an indifferent universe, the act of reaching out still matters. It matters because it defines who we are, a species that wonders, that questions, that hopes, that looks up at the stars and refuses to accept that they're empty, that sends messages into the dark not because we know they'll be received, but because we believe they should be sent. There's a kind of faith in that. Not religious faith necessarily, though it connects to the same deep human need for connection and meaning, but faith in the possibility of understanding, faith that intelligence, wherever it emerges, shares certain fundamental qualities: curiosity, the desire to communicate, the hope for connection, faith that we're not just talking to ourselves when we broadcast into space, that somewhere, maybe, someone is listening, or will listen, or at least that the effort of speaking matters regardless of whether it's heard. And maybe that's the real answer to our original question. Did we trigger 3I/ATLAS? Probably not. But did our reaching out matter? Did it change us, shape us, push us toward thinking about ourselves in cosmic terms? Yes. Absolutely yes. Every message we've sent, every signal we've broadcast, every artifact we've launched into space, these have changed who we are as a species. They've forced us to think about how we present ourselves to potential observers. They've made us consider what we want to be known for, what we want to communicate about humanity. They've pushed us toward better behaviour, or at least toward awareness of our behaviour. It's harder to be casually destructive when you imagine explaining your actions to an alien anthropologist. It's harder to ignore long-term consequences when you think about them from a cosmic timescale. They've connected us to something larger than ourselves, made us part of a cosmic conversation, even if it's a one-sided conversation so far, given us a sense of participation in something that extends beyond our planet, our lifetime, our civilization's current phase, and they've given us hope. The hope that we might not be alone, that our signals might be heard, that someone somewhere might care that we exist. That hope sustains us through the silence, through the decades of listening without hearing, through the long wait for a response that might never come. Because hope doesn't require certainty, it just requires possibility. And the universe we've discovered, full of planets, rich in the chemistry of life, governed by universal physical laws, is a universe full of possibilities. So we continue, reaching out, broadcasting, sending our messages, building our artifacts, expanding our presence, not because we know it will work, but because it might, because the possibility is worth the effort, because reaching into the dark and saying, "Hello, we're here," is what we do. It's who we are. And someday, maybe someone will answer. A signal from the stars, a visitor from beyond, a confirmation that we were heard, that we're not alone, that our reaching out mattered. Or maybe not. Maybe the silence continues. Maybe we remain isolated by distance and time and the vast emptiness between stars. But either way, we reached out. We tried. We made ourselves known. And in a universe as old and vast and generally indifferent as ours, that act of reaching, that refusal to accept isolation, that hope for connection, might be the most beautiful thing we've ever done. Whether anyone noticed or not, whether 3i/ATLAS is natural or artificial, whether our signals triggered anything, we sent them, they're travelling, carrying us into the cosmos, and that, in itself, is enough. Thank you for staying with me through this long contemplation. We've travelled together from the discovery of a comet to the edges of possibility, from the hard facts of orbital mechanics to the soft uncertainties of cosmic connection. We've explored radio waves and nuclear flashes, deliberate messages and physical artifacts, the ethics of noise and the meaning of being seen. And we've circled again and again around that central question. Did we accidentally trigger 3i/ATLAS? The answer, as honestly as I can give it, is probably not. The universe is full of natural explanations, and 3i/ATLAS fits them well. A wandering comet, a random encounter, interesting timing but ultimately coincidental. But quote 24 isn't certainly not. And in that gap between the probable and the certain, there's room for wonder, room for possibility, room for the recognition that we live in a universe that might surprise us, that might be more connected and responsive than we assume. And whether we triggered this specific visitor or not, we've triggered something larger. We've triggered our own transformation from a quiet species to a loud one, from cosmically invisible to potentially detectable, from isolated to reaching out. That transformation is real. The signals we've sent are real. The artifacts we've launched are real. The footprint we've created, electromagnetic, physical, chemical, is real and growing. We've made ourselves known to the universe, and now we wait to see if the universe responds. If you enjoyed this slow drift through cosmic questions, a like and subscribe helps others find their way to these contemplations. And if you have thoughts, questions, or your own theories about interstellar visitors and cosmic communication, the comments are always open. I'd love to hear what you think. Wherever you are in the world, whatever time it is, I hope you're comfortable now. I hope your breathing has slowed, your thoughts have quieted, your body has relaxed into rest. Look up at the stars if you can see them from where you are, or imagine them if you can't. All those points of light, all those possible worlds, all those potential minds looking outward, wondering, hoping, reaching into the dark just as we do. Maybe our signals have reached some of them. Maybe someone out there noticed. Maybe in ways we don't yet understand we've made contact. Or maybe we're still alone, still waiting, still broadcasting into silence. But we're broadcasting, we're reaching, we're trying. And in the vast ancient cosmos, that effort, that hope, that refusal to accept isolation might be the rarest and most precious thing of all. Sleep well, dream of stars and signals and the possibility of voices in the dark. Good night.